I mentioned early on that one of the goals for Calculus 3 in my mind is to get to the point where we feel we can calculate anything. Whether we're accurate about that, maybe we don't know, but particularly the geometric things: volume, area, arc length, and angle. Those are the geometric measurements that we are most familiar with. And so tonight I want to concentrate first on angles. And then I also want to switch over and start doing parts and derivatives a lot. So anyway, to that end, I had originally decided not to hand out this supplement, but I decided I wanted this picture. Now, it really is logically prior to supplement 3, the partial derivatives. So I call it supplement 2.5. I guess you only need one. I don't want to send somebody up here on an expedition. So I talked about parameterized curves and vector parameterized curves and all that stuff. And one of the things we can do with those is to calculate length of the curve and angle between curves. And we've done a whole lot of length now, and I'm tired of length, so we'll do angle for a minute. So to that end, I want to look at problem 6. So in problem 6, it says the parabola in the YZ plane. How does the grammar work here? Oh, the parabola in the YZ plane given by z equals y squared, and the helix defined by this other function here intersect at a single point. And so I want to find this point and find the angle at which they intersect. Okay? So my two equations here, we've got z equals y squared. And this is in the YZ plane. And the other one is the helix. We've got R of t equals 2 sine pi t I plus 2 cosine pi t J, and then plus pk. So I've got a picture of the parabola and the helix there. Helix, basically, if you just look at this part right there, you get a circle. Let me just use x and y the way we think about them in the beginning courses. So here's the x-axis horizontal, the y-axis vertical, and then the z-axis will be coming out of the board. So looking at this circle, if I didn't have this part right here, I'd just be getting a circle in here. Now, it wouldn't be counterclockwise the way we usually expect it, because when we have cosine on the x and sine on the y, then we get counterclockwise. But when I switch around this way, when t is 0, I've got x is 0, but the y would be 2 times 1. So it starts up here. And then when t is pi over 2, we'll have the cosine of, or no, not pi over 2, when t is 2, when t is a half, that's what I want. When t is a half, I'll have the cosine of pi over 2, which is 0. And here I have the sine of pi over 2, which is 1. Well, so that's x is 1, y is 0. So here is t equals 0. And then here is t equals 1/2. And it starts out going like this. But now let's put the z back into it. Z equals t. So yeah, again, it's xi plus yj plus zk. Okay. So x is this. Y is this other one. And z equals t. So while this much right here is doing the circular motion sort of thing, at the same time, this thing is coming out of the board. So it's working like this. A helix, or a spring. So anyway, that's that thing. And you can see it on here. Oh, let's see, somebody just walked in. Okay. Attendant? Yeah, that's reminding me. Oh, okay. Well, I'll wait a few more minutes because so we don't have 18 yet. They were close. But yeah, let me get that out of the book. All right. So now I cannot possibly draw this, and you know, you've got something to stare at already. But anyway, the usual position here is x coming out of the board, and we're going. We're starting at y. That's right, and then so it's going around like this, and then we've got our parabola. And we want to see where do they intersect. And I've already told you they intersect in one point. So can you see where that point of intersection is on here? It's kind of hard to tell because, you know, it's in 2 dimensions and we're trying to do a 3-dimensional picture on a 3-dimensional object, but we're drawing a 2-dimensional picture of it. But anyway, it's this point right here. Not at the very top loop in blue, but that first green loop. That's where it's going to be. And down in this third loop, the parabola is inside of the helix. And then at the top loop, it's outside the helix. And right there in that stuff close to where it says 4, that's where it intersects. But we can figure that out just on the basis of this. So look, we got z equals y squared. And the thing is, the helix has a radius of 2. All right? So wherever they intersect, it's going to have to be in a distance 2 from the z-axis. And here's the other thing. It's in the yz plane, so that's x equals 0. By the way, if I did not throw in x equals 0, I wouldn't have a parabola. A parabola is a curve, but I wouldn't have a curve. I'd have a surface. So this is what z equals y squared looks like. It's a sheet of paper curled up to where the cross section is a parabola. But if I just look at it at x equals 0, then that's that curve. So I've really got several equations going here. But starting with x equals 0, put this one equal to that. So 2 sine pi t equals x, but that also equals 0. So this is for the intersection. Well, what that says is that our sine, then I just divide by 2, and our sine is 0. And for what angles is the sine equal to 0?
0,
Pi, 0, pi, 2 pi, 3 pi. So t has to be an integer. So we just try. Well, how about t equals 0? How about t equals 1? How about t equals 2? So let's see. Look at the y now. So if I have an integer, the cosine of, pi t, for t an integer, is plus or minus 1. If t is even, you get plus 1. If t is odd, you get minus 1. And so then when I multiply that by 2, which is the y is going to be plus or minus 2. And that being the case, the z is t. It has to be t equals, well, I mean, just try one after the other. So if we have t equals 0, then we're looking at 0, comma, 2, comma, 0. And if we look at t equals 1, we're looking at, let's see, x would be 2, y would be 0, and this would be 1. And then for 2, I'm sorry, halves. So this is for pi over 2. And at 1, then we're going to get the minus 1, minus 2 here. And this is 0, and this is going to be 1. This is half. And then let's see. 3 halves and 2. T is an integer, not a half integer. I'm so sorry. 1, 2, 3, 4. Here it goes. So what I was thinking we were going about pi over 2, but these are zeros here. And so we get a minus 2, and then we get a plus 2, and we get a minus 2, and a plus 2. And there it is, because the z is supposed to be y squared. I'm sorry I'm making such heavy work out of that. I mean, you can just see from the picture. If that's the point, well, that's z equals 4, and z is the same as t. So it had to be t equals 4. But anyway, that's the reasoning such as it is. I'm not really all that concerned with finding the intersection point. We've done a lot of that already. But I want the angle. We've done some of that, but not angles between curves. So we're looking at t equals 4, and we're looking at the point 0, 2, 4. And how do you think it is that we're going to calculate the angle?
The angle
between the parabola and the helix.
In radians.
Well, yes, it's in radians. It can be radians or degrees for that matter.
Which point are you talking about?
At that point, see, this is the only point where they intersect. And so we got the parabola coming up like this. And we've got the helix sort of coming in like that, so we're looking at an angle kind of about like that. So less than 90, probably. And I'm saying, what kind of techniques are we going to use? I didn't really mean what kind of angles, like radians or degrees or whatever, but what kind of technique do we use? What's available to us in calculus 3? What? Vectors, okay. So, in fact, here's a vector right there. There's a whole bunch of vectors. That's a vector value function. And to get the angle, I need to have the vector that points along the curve. How do I get a vector pointing along the curve?
Right through the perpendicular both of them.
Derivative. I'm going to use a derivative. So these vectors point from the origin to points on the curve. And so this gets a little bit higher, a little bit higher, a little bit higher, etc. When you're using a vector valued function to describe a curve, the vectors themselves all point at the origin, and the heads of the vectors, I mean the bases, the tails of the vectors are always at the origin, and the heads of the vectors describe the curve. But when I take the derivative, I'm going to base the derivatives on the curve itself. So here, here, here. So we need the derivative. So let's get the derivative. R prime of t equals 2 pi times the cosine of pi t. And then take the derivative of cosine, we get a minus 2 pi times the sine of pi t, j. And then here, we're taking the derivative with respect to t, so all that is just k. So they all have some upward component, and then these things, well, it's sines and cosines, so it's just sort of wrapping around, but with slight upward component from this. And what about the other one? So let's see, we need one vector. T is 4, so we calculate r prime of 4. So we're going to get 2 pi times 1I minus 2 pi times 0 j, and then plus k. So this is just 2 pi I plus k. So that's one of our vectors. Let's call that one A. And B, that'll be along the parabola. So I want to get a parameterized curve for this one. How can I parameterize this? And hint, it's a function of y.
Equal to t squared?
Z would be t squared. Except we probably shouldn't call it t squared, because z equals t on this curve. It's like when we were doing the intersection between two straight lines. We want an intersection. We don't care about a collision. So I'll use a different parameter name. I'll call it s. Or I could even call it y. But I think I will call it, let's just call it s. And then y will equal, I'm sorry, z will be s squared and y will be s. And x, what's x?
0.
0. Right. So then we have this other vector value function, I'll call it f. F of s is going to be 0I plus sj plus s squared k. And so when I take the derivative, f prime of s, I'm going to get j plus 2sk. And what do I need for s? At the point of intersection, what's s?
Oh, it's not gonna be the same number.
It's not going to be the same number. That's why I had to use a different letter.
Right. So you know that y is 2, so s will be 2.
S will be 2.
And
I'll calculate f prime of 2. And so I'll get j plus 4. Okay. All right, and I'll call that one b. So now we just go ahead and calculate the dot product and all that mess. So a dot b over magnitude a, magnitude b, and this will be the cosine of theta. What's a dot b?
a dot b.
Yeah.
Sine theta? Or is it A?
Oh, okay. So you're telling me the formula for the magnitude for the dot product in terms of length and angle, and it is magnitude times magnitude times.
Say it one more time.
What's the geometric interpretation of dot product?
Geometric. Oh, dot product. And then the scalar.
It is a scalar, and geometrically, if I know the magnitudes of the vectors and the relative direction, which is to say the angle, it's magnitude times which trig function?
Cosine.
Cosine theta, which is why I just wrote this one down here.
Yeah.
So when I asked what's the dot product, and she thought I was thinking, well, you know, how do you describe
Oh,
a dot product?
it's the vectors, right? You multiply the vectors and add them?
I multiply the components and add them, yes.
I should know.
But what I was really asking is, what do you get?
Oh, 4.
4. Let's see, is that right? Here it is. Yep, sure enough. So I've got a dot b. Grid in my chart here. A dot b. I've got that one. And that one over there. 2 pi I plus k. And then I'm dotting that with j plus 2k. 4k.
Okay. So it's 0 times 2 pi, which is 0.
Mhm.
And then 0 times j.
Mm-hmm.
No, 0 times 1, which
So 1.
is 0. And then 1 times 4, which is 4.
Yeah.
And all of that.
So we get 4. And again, sometimes people really have a much easier time thinking of it in terms of the brackets.
Yeah.
So I don't mind doing that. But you need to get more and more to the point where you can handle it in either notation. Anyway, 0 plus 0 plus 4. So here I get 4. What's the magnitude of A? Magnitudes have those square roots.
Square root of 4 pi squared plus 1.
Got it? And the other one is just
Square root of 5. No, square root of 17, 17.
15. There we go. Etc. So now you just have to take the arc cosine and get a number, an angle. And I didn't bring my calculator, mercifully enough. So I wanted to do one where in 3 dimensions we've got to do all the parameterization stuff, and I thought this was a reasonably good example, and I already had the picture on my computer. I did the picture with Maple software back when the college was supporting Maple. They've let that license lapse, so I've just been using this picture for several semesters in a row. Anyway, I now want to do a 2-dimensional example. I deliberately did a 3-dimensional example first, but let's do a 2-dimensional example. And let's see, I'm going to pull an example from supplement 2. If I can find supplement 2, it's in here. And I guess everybody's here is gonna get here, so I'm gonna take this little sheet now. So in supplement 2, this is problem 26 on supplement 2. I want to find the points of intersection and the angles of intersection for the curve y equals x cubed and y equals 4x. Y equals x cubed and y equals 4x. Well, actually, I don't have to find y equals x cubed, there it is. But, I mean, find the intersections and angles. Well, we know what y equals x cubed looks like. We know even better what y equals 4x looks like. Alright, so here's my y equals 4x. Let's see, 2 points of intersection? Let's think about that. I've got, when I put these equal, I'm going to have x cubed equals 4x, that's a cubic. How many? Oh, there should be 3. Should be 3. And so, wait a minute. One of the intersections is at the origin. 0 cubed is 0, 1 cubed is 1, and then we just come up here somewhere.
And then there's one on the bottom.
Right. Okay. So, what point would this be?
About 2.
2.
2,8.
2,8. Well, I forgot the 2. I just and then this one, by symmetry, minus 2, minus 8.
Oh.
And what do you think is going to happen? I'm going to get a fairly big angle here, and a fairly small angle up here. And by the way, of course, I've got vertical angles basically. So these two angles are the same. And what about the angles down here? Again, they'll be the same. And they'll also be the same as those because of symmetry. So really, what now?
Can you draw where the angle, like where the angle you're looking at?
Yeah, well, let me try.
Just so I can see. Like what?
So I'm looking at this angle right there.
That looks like
Or this angle.
okay. They're the same thing as what you're saying.
Yeah.
Okay.
Vertical angles are equal. That's the theorem in geometry. Now, what do I mean by an angle between a line and a curve?
The vectors?
The vectors, yeah.
The angle between them.
Or the tangent lines, either way. So, I'm going to look for a couple of vectors then. I want a vector up here, and I want a vector along here. And of course, the vector along the line is actually part of the line. So, if I did everything the same way I did over here, then I need parameterized curves. Or, excuse me, parameterized line and parameterized curve. So if I'm looking at y equals x cubed, how do I get a parameterization? I need an x equals and a y equals.
X equals the cube root of y.
X equals what?
The cube root of y.
I could do that.
X equals 2, y equals 8.
X equals 2, y equals, well, yeah, but I want, that would only be this point. I want it all along here. So I need some variables. She suggested using y as a parameter and letting y equal y and x equal the cube root of y. I got an easier way. Instead of letting y be the parameter, I use x, then I don't have to do cube roots. And again, if you're squeamish about using a parameter, using a coordinate as a parameter, you can always call it t instead. And then this would be tq.
Yeah, I was
And then we have r of t would equal xi plus yj. So that'll be ti plus tq j. And there's our parameterization. Now, we could do the same thing for the other. But can't you just sort of figure out what a vector along that line would be? Let's see, we're going from 0, 0.
4.
What now?
4.
But that's not a vector, that's a number.
2, 8.
2, 8. Yeah. So if I went like this with 2, 8, well, I can just move that on up here and it would be 2, 8. But if you want to, you can go ahead and do the parameterization the same way. So I can let x equal, and this time it'd be okay to use the same parameter. Over there, I couldn't use the same parameter because the parameters were different at the same point. But if I use t, I'll have x equals 2,
And then y is equal to 14.
and then y is equal to 14. And so now I take the, let's see, what is it? I do f of t equals ti plus 4tj. And now I need the derivatives. So over here I've got r prime of t equals 1i, or I, plus 3t squared j. And so I want that at 2. And so that's going to be I plus 12. And over here, f prime, when it's a straight line parameterized uniformly, then you don't even need to evaluate it. It's just going to be I plus 4j. Oh, I thought it was supposed to be 2 plus 8, 2i plus 8j. I don't care. It's in the same direction. So it'll be perfectly okay. Because what happens when we do our cosine, we'll be dividing by the magnitude anyway. So it's like I take this unit vector and I dot it with this other unit vector. All right. So anyway, let's get the job done here. And again, I might as well say, okay, I'm going to do f prime at 2. But if I wanted to do f prime at 17, that would have been all right also. I plus 4j. And again, let me emphasize one more time, it was okay to use